So hello everyone, welcome you all to live session 7 of NPTEL course Fluid Flow Operations taught by Professor Shubhrata Kumar Majumdar. My name is Nagpan Saikama, I am the teaching assistant for this course. So last week we discussed about different losses in pipes. So we also discussed different reasons which could be causing the losses. So one reason is friction losses. Whenever there could be friction between different layers of fluid, and also there will be friction between fluid and walls of the pipe as well, pipe or geometry. So that would be one reason why there will be losses in pipe, and the second reason is that because of the change in geometry. Okay, and also because of the presence of walls and also joints, there will be losses in the pipe as well, like loss in energy. So this week we'll be discussing about flow in channels. So which basically includes flow in open channels with constant section and also constant flow velocity. Then we'll also look at the optimum shape for an open channel as well. Okay, so what is a water channel? What is a water channel? So the channel where a stream of water flows with a free surface and it should be exposed to air. So this is called a water channel. Okay, it should have or a channel where a stream of water flows with a free surface exposed to the open air. So this is the simple definition of a water channel. So water channel have a large hydraulic depths. That means Reynolds number will also be very large. Okay. So that means basically this is where turbulent flow. So they have hydraulic mean depth. So we know that Reynolds number is U into D into rho by mu. Basically, velocity into diameter into density by viscosity, right? So if d, that is hydraulic distance or hydraulic diameter, okay, in this case we'll use hydraulic mean depth. Okay, whenever there's a channel, or let's say you can also consider a water canal as a water channel as well. So basically, these water channels or water canals, whenever they are flowing, they'll be having depth, right? Instead of diameter, we will also be having depth, right? So over here we'll consider hydraulic mean depth. Okay. So if these water channels having higher diameter, that means Reynolds number will be very high. So large hydraulic diameter, hydraulic mean depth, which indicates large Reynolds number. Okay. So this also implies that the flow will be a turbulent flow. Okay, so because of this high Reynolds number or larger higher Reynolds numbers, the friction coefficient becomes constant and it is determined by the roughness of wall. So we have already discussed this in the last class, how Reynolds number or roughness of a surface will be impacting the friction losses. So because of this high Reynolds number, friction coefficient becomes or is constant and is determined by the roughness of the wall. Okay. So let's look at flow in open channel with constant cross section and also constant flow velocity. Okay. So constant section indicates that this cross section area of the canal or water channel is constant, and the water or fluid inside this water canal is also flowing with a constant velocity. So in an open channel, the flowing water will always be having a free surface, right? That is, which is open to the atmosphere, and it will be flowing with the help of gravity. So let's take an example. So let's say this is the bottom part of the canal or water channel, which is at an inclination. It's with the horizontal, it is making an angle theta. Okay, let's say this angle is theta. Okay, and this is the open surface of the water. Okay, let's take a cross section, and let's say the length of this cross section is L. Okay, and water is flowing with a velocity of let's say V. V is the velocity of water, and whenever water is flowing, so the direction of flow is in this direction, right? So whenever water is flowing, there will always be opposite force acting, right, near the wall. So this is because of the friction. So let's say this is tau naught is the opposite force that is acting on the water, and let's say because of mass of water, as this is at an inclination, there will also be mass force, right? And obviously there will also be pressure force as well. Let's say opposite forces are F2. Okay, all the opposite forces in combined, let's say they are F2, and the forces which are helping for the water to flow is F1. Okay. Assume that water is flowing with a constant velocity V, constant velocity V in an open channel, and let's say inclination angle is theta. Inclination angle at bottom face is theta. Okay. And we also assume that the cross section area or the cross section of the channel is constant, right? Okay, this is also important because if the cross section is changing, again flow rate will change and also velocity will be changing, right? So that's why we are assuming the area to be cross section area to be constant. Okay, and also the depth of the water is also constant, constant velocity, inclination, cross section area, and water depth is also constant or uniform. Okay, and let's say this forces F1 and F2 are acting. These are because of the hydrostatic pressure balance. Okay, one is because of the weight of the water flowing, and the other one is because of the pressure forces. Okay, so here because of the inclination, the weight of water will be helping the flow of water, or it will be acting along the direction of flow of the water. Okay, so as a flow is having uniform cross section, oh sorry, as a flow is having uniform velocity, that means it is not accelerating. Okay, so that means all the forces should be balanced each other, like the forces which are helping for the flow and the forces which are acting in the opposite direction, they should be balanced because there is no acceleration. As acceleration is zero, forces must be balanced. Okay, so our net forces should be zero, right? Okay, so let's balance the forces across this cross section. Okay, let me redraw it. This is the bottom surface of the channel, and it is making an angle theta. And this is the cross section that we are considering. And let's say the length of this cross section is L. Okay, and we have two forces, one which is helping for the flow, and the other one which is opposing the flow. And let's say this is a free surface, right? Let's say the velocity is v. Okay, so we already established that the cross-section area of the channel is constant, right? So let's say, for example, A is the cross-section area, or let's say constant of the channel. Let's say it is A. Okay, and let's say weighted perimeter of the channel. Let's say it is represented by S. Okay, we already discussed the weighted perimeter in the last class. Okay, and also the shear stress that is opposing the force is tau naught. Okay, this is tau naught. So how do you balance these forces? So first one is weight of the force, which is helping the flow, right? So that will be density into volume, that is A into L will be the volume. Okay, and we have gravity, let's say G. Okay, the density into volume into gravity will be the weight, and its component will be sine theta, which is acting in this direction. Okay, and what is the opposite force that is acting here? That will be tau naught into S into L. Okay, so as theta is small, so in flow channels or in canals, there will not be a steep inclination, right? So that will be a small inclination, right? So theta is very small. So that means we can assume tan theta as, or tan theta will be almost equal to sine theta. So let's say this is I. So in that case, tau naught will be equal to, let me rewrite the equation. Let's say this is equation 1 and this is equation 2. Let me write the equation 1. So rho into G into A into L, that is density into gravity into volume into its component sin theta will be equal to tau naught S L. Okay. So now we can write this as tau naught is equal to, so just separate the variables. You will be getting tau naught is equal to rho into G into A by S into I. Okay. Instead of sin theta, I'm just writing I. Okay, so you can either write As theta is very small, we can also replace this with tan theta as well. Okay. So this will become rho into G, and this is, let's say, A by S, we'll call it as M. Okay. This is nothing but hydraulic mean depth. Area of cross section divided by wetted perimeter, it is hydraulic mean depth. Mean depth. Okay. And let's say this is equation. Uh, this will become rho into G into M into I. Let's say this is equation 3. Okay. So in the last class, there were a couple of equations, right, for tau naught. So we'll recall that equation. So we'll write tau naught in terms of friction coefficient. So in that case, tau naught will be equal to F into rho V square by 2. Okay. And let's say this is equation number 4. So just substitute this in this equation. Substitute 4 in 3. So we'll be getting F rho V square by 2 is equal to rho G M into I. This is equation 4. Sorry, this is equation number 5, right? Okay. So if you simplify this and write it in terms of V, what would be the equation? V is equal to square root of rho gets cancelled out. Okay. We'll be having 2 into G M I by F. Okay. So let's say this is equation number 6. And here F is fanning friction factor. And just to avoid confusion, let's say F is fanning friction factor and delta as Darcy friction factor. Fanning friction factor F, and this is Darcy friction factor DFF. So, and what is the relation between F and lambda? F will be equal to lambda by 4, right? Fanning friction factor will always be 1/4 of the Darcy friction factor. This also we discussed in the last class. Okay. So let's write equation number 6 again. What was equation 6? V is equal to, this is equation 6. V is equal to square root of 2G by F into Mi, right? So let's say this is constant because fanning friction factor, gravity, all these are constant. So let's say this is, let's represent it as C, which stands for constant, into square root of Mi. So let's say this is equation number 7. And here C stands for square root of 2G by F. Okay. So this particular equation, equation 7, this is called Cizzy's formula, and C is the flow velocity coefficient. And there is a empirical formula as well to calculate C. We'll come to that. This equation, this is called Cizzy's formula, and C is called flow velocity coefficient. Okay. So C can be calculated. Just a second. So C can be calculated using two equations. One we have Cutter equation, and the other one is Bézier equation. So let me just write both the empirical formulas. So first one is So here C can be calculated from this equation. So C will be equal to 23 plus 1 by n plus 0.00155 by I divided by 1 plus 23 plus 0.00155 by I into n by square root of m. Okay. So this is one equation. Let's say this is equation 8. And the other one is Bayesian equation. So the empirical formula for calculating C using Bayesian equation is C is equal to 87 by 1 plus alpha by square root of m. Okay. So for both these formulas, or for using for both these empirical formulas, we need value of. So in this equation, we need a value of alpha, and here we'll be needing value of n. Okay. So both n and m, they depend upon the material. Okay. So the material with which they are preparing the walls of the channel. Okay, so it might be cement, or it could be a concrete. It could be made out of concrete, or it could be made out of some smooth cement. Okay, like some kind of smooth cement coating, or it can also be concrete with exposed gravel. So depending on the material, the value of n and alpha will change. Okay, so let's see a couple of materials along with their n and alpha values. So let's take non-finished concrete. Okay, and this is value of n, and this is alpha. Okay, so for non-finished concrete, n value varies from 0.015 to 0.018. Okay, and this they did not perform any experiments, or they did not calculate the value alpha value for this material, so we cannot use Bayesian equation for this particular material. And there are also other materials. As is an empirical equation, they'll be doing experiments, and from there they have derived this equation. Okay, so for non-finished concrete, they must have not performed any experiments, so we don't have any value for alpha. So we cannot use Bayesian equation for this material to calculate value of C. Okay, we have to use for the first equation. We have to use the first equation, then calculate. And then if we go for something else like concrete with exposed gravel, concrete with exposed gravel. So if this is the material of the channel, then value of n will be between 0.016 to 0.02, and value of alpha is 1.3. Okay, this they have performed. And if you go for something else like, let's take bending rivers with large stones and wild grass. If the surface is covered with large stones and wild grass, so in that case, and value of alpha is 2. Okay, so similarly, they have performed experiments with different materials, and they have come up with these empirical equations and also values of the constants. Okay, so we have many other materials, so you can just refer literature for that. Okay. And also we have one more equation, that is Manning equation for calculating velocity in a channel. Okay, so V is equal to 1 by n into m power 2 by 3 into I power 1 by 2. Okay. So there is one more equation for calculating flow velocity in an open channel. Okay. So in general, okay, so most of the cases, flow velocity will be between point 0.3 to zero point 0.5 to 3 meter per second in an open channel. Flow velocity will vary from zero point 0.5 to 3 meter per second. And so using this velocity, you can also calculate the discharge as well or the flow rate as well. So how do you calculate it? Q will be basically Q will be equal to what is formula for discharge or flow rate? What will be the formula for discharge or flow rate? You can write it in the chat box if you know. What will be the flow rate for? What will be the formula for flow rate? Q is equal to Q is equal to density in sorry area into velocity, right? Yes or no? Okay. So Q is equal to area into velocity. Okay. So area of cross section we already know it is a constant area cross section. So area into what will be the formula for V? Let's substitute this equation, that is equation number 7. It will become C into square root of mi. Okay. So this can also be, so you can also substitute this equation, that is equation number 10. So in that case, we'll have a 1 by n into a into m power 2 by 3 into I power 1 by 2. Okay. So let's say it's equation number 11. Okay. So this is how you will be able to calculate flow rate and also, sorry, this is how you'll be able to calculate velocity and also flow rate using the velocity. So let's also look at optimum section shape for an open channel. So we already assume the area of section to be A, right? So let's also consider the same thing here. Cross section area as A. Okay. So let's say if A is a cross section area of open channel and this is constant, and from this equation if we are also uh, yeah, from this equation if we also have values of C and I, that means section shape is perfectly or properly selected. Okay, so that weighted perimeter should be minimized. Okay, and at the same time both flow rate and discharge should be maximum. Okay, in that way you have to design your channel section. Okay, one, S should be minimum, weighted parameter should be minimum. Two, your velocity should be maximum, and also flow rate should be maximum for a given values of I and C. Okay, these are constants, right? For these given values, you have to select a column or not column. You have to select a channel in such a way that you'll be able to optimize these values. That should be minimum, V should be maximum, and Q should be maximum. Okay. Out of all the geometries, if you're fully charging this channel, that means if flow is complete in this channel, a circle has the shortest length of weighted perimeter, or it has the shortest value for weighted perimeter for a given value of A. Okay, so these are all calculations are already done for a given, even for a sphere. You know that why do you use spheres for storing gas in or LPG? If you observe any plant, okay, or let's take another simple example. So whenever water is flowing, it will be, or whenever the raindrops, they will be taking shape of a water circular shape, right? So why is that? Because the surface tension can be minimized, okay, for circular geometry or sphere geometry. So in the say similarly here in this case, for a given value of A, okay, or given for given cross section area, the weighted parameter will be shortest for circle. Okay, so so that is why we'll be using round channel for round channel. If we are supposed to have minimum surface area or minimum contact, minimum hydraulic or weighted parameter, maximum velocity and maximum flow rate. Okay, so let's see this case that is circular water channel. This will be similar to that of a pipe flow. Okay, okay, let's say this is a circular channel and R is a radius and this is theta. This is where water is flowing. Okay, so let's consider a relationship between water level, flow rate, and discharge as well for this round shaped or circular shaped water channel. So first let's write down the radius of, so let's say the radius is R for this particular channel and area of cross section, let's say this A. Okay, so if you recall this equation, equation number 10, let's write it down. So V is equal to 1 by N into A by S power 2 by 3 into I power 1 by 2, right? So if you substitute this in Q is equal to VA formula, we'll get Q is equal to 1 by N into A power 5 by 3, right? By S by S power 2 by 3 into I power 1 by 2. I power 1 by 2. Okay. So I just substituted V is equal to this formula in this equation. So as we are having extra A here, it will become A power 5 by 3 and the other terms will be same. Okay, so let's say this is equation number 12. Okay, so what would be the value of A? So that is this particular area or area of the sector, that will be R square into, these are all mathematical formulas, direct formulas which I am taking. R square into theta by 2 minus R square into cos theta by 2 sin theta by 2. Okay, so this will give us R square into theta minus sin theta by 2. So we're just trying to, okay. So here weighted parameter R will S will be equal to R into theta, that is radius into theta, and M will be equal to, for this particular geometry, that is circular geometry, M will be equal to R by 2 into 1 minus sin theta by theta. Let's say this equation number 14 and 15. Okay. So if you substitute values of R and S in this equation, we'll be getting V is equal to 1 by N into, let me just write down the equation first, is equal to 1 by N into A by S power 2 by 3 into I power 1 by 2. Okay. So substitute this in this equation, we'll be getting 1 by N into I power 1 by 2 into what is A. So let's divide these two equations, 13 and 14. 14 by 13, we'll get R square into theta minus sine theta by 2. So this will basically give us A by S. Okay. 14 by 13 will give us A by S. So A by S will be equal to R square by R square into theta minus sine theta by 2 by R theta. So R gets cancelled out and we will be left with R by 2 into, we can also divide it by theta. So this will become 1 minus sine theta by theta whole power 2 by 3. And similarly, flow rate will be just multiply area Q is equal to V into A, right? So just multiply area into 16. We'll be getting 1 by N into I power 1 by 2 into, you just have to multiply this term. So it becomes, I'll write down the final equation. So just cross check this equation once. So this will become 1 by N into I power 1 by 2 into theta into R power 8 by 3 by 2 power 5 by 3 into 1 minus sine theta by theta whole power whole power 5 by 3. Okay. That's the equation number 17. So this will be the flow rate and also velocity and flow rate of water in a round shaped or circular shaped water channel. So let's say if UF and QF, okay, if these are the flow rates and discharge at maximum capacity, or let's say flow velocity and at maximum capacity. So in that case, V by V full or VF, let me write this V. Okay. So V by V full will be 1 minus sine theta by theta power 2 by 3. Okay. Again, we also have a graph for theta. Okay. So if you increase the theta, how would Q by Q full and V by V full vary? Okay. So the graph looks something like this. So let's say this is 0.5 and this is 1. So Q by Q full varies something like this. So it will pass through, it will overshoot value of 1 and then it will finally come to 1. And V full also looks something like this. Will be following the same behavior. It will be overshooting value of 1 and then it will be finally coming to 1. Okay. This maximum value will be 1.2. Okay, so this is how you calculate V by V full. So if you have value of one parameter, you can calculate the value of other parameter. Okay, into again going into derivation, it will be again complicated. So I'm just writing down the formulas. Q by Q full will be equal to theta by 2 pi into 1 minus sine theta by theta whole power 5 by 3. This is equation number 20. So this is for the open channel. Okay, but there might be cases where circular channel will be obviously the best thing to go. But let's say if you have any other requirement, or let's say if there was already a channel which was built in a different shape, let's say for example rectangular shape. So how do this flow rate and velocity will change? So let's also see rectangular channel. Okay, so here we have rectangle channel. Okay, so one end is a free end. This is a free end. So the water is flowing. Okay, so water will be flowing in this direction. Okay, this is something like this. Okay, so again, area of cross section is A, and let's say the distance between two extremes is B, or breadth of the channel, and the height of this or depth of the water is flowing water is H. Okay, so for the case of rectangle channel section, so S is going to be it is weighted perimeter is going to be the breadth, it is touching the breadth, right? So B plus H into H. Okay, B plus H plus H. Okay, so this is going to be B plus 2H. So if you take differential of d of S with respect to H, it will become. Let's do one more thing. Instead of having these many parameters, A is anyway constant, right? So let's write this in terms of A. So A is nothing but breadth into height, right? This is a rectangular channel. So area is going to be breadth into height. So let's eliminate one parameter. So let's eliminate breadth in this case. So breadth will be equal to A by H, right? So just substitute this here. You'll be getting A by H plus 2H. That is equation number 21. Okay. So now if you take differential of S with respect to H, you will be getting minus A by H square plus 2. Okay. So if this has to be minimum, okay, if the value of S or the value of weighted parameter, if this value should be minimum, what should be the relation, or what should be the value of ds by dh? It should be equal to 0, right? For a term, for a value or for a parameter to be maximum minimum, its differential should be 0, right? So just equate this to 0 and you will get value of a. So that implies a will be 2h square. That is equation number 22. So if this follows, if area is 2 into h square, then the value of the rectangle channel, or the value of weighted perimeter for this rectangle channel will be minimum. Okay. So you have relation for A and H, then you can also calculate B, right? So in this case, B will be equal to H by or you can also write B by H or H by B will be 1 by, oh sorry, B will be 2H. Okay, B is equal to 2H. So H by B will be equal to 1 by 2. That's equation number 23. Okay, so if you have value of I, C, and A, okay, if these values are constant, then in order to maximize velocity of, in order to maximize U and Q, depth should be equal to, or H should be equal to half of the width. Okay, so if this is followed, then U and A can be maximum. So this is how you will be designing a rectangular channel. So in order to have maximum flow rate or maximum velocity, height should always be half of the breadth. Okay. Okay. So do you have any doubts until now? Do you have any doubts? Any doubts until now? If you have any doubts, you can post them in the chat box, or you can unmute yourself and ask me. Any doubts until now? Okay. So if you don't have any doubts, then let's move on to the next topic. It is equation of specific flow. Oh, sorry, equation of specific energy. Okay. So let me draw the channel. Let's say this is the bottom cross section or the bottom part, and this is the vertical line. And this is the bottom level or reference level. Okay. So whenever there is a flow, there will always be three components of energy. Okay. So One will be because of the elevation, okay, the other one will be because of the pressure, the third one will be because of the velocity or because of the flow. Okay, so it will be having three components. One is because of height, okay, that is potential energy. The other one will be because of the pressure, that will be P by rho g, and the other height will be because of the velocity, that is v square by 2g. Okay, so total head will be equal to v square by 2g plus P by rho g plus z plus also this elevation, okay, plus z naught. Okay. So here P is the pressure in the open channel at any point. Okay, and at any point P is the pressure energy. Okay, if the depth of the water channel is given, then water channel is H. So in that case, H will be P by rho g plus Z. Okay, let's change the equation number one, and let's change the equation number two. Okay, so we can also say total head. We can also write total head in terms of this thing. Total head. You can also write in this equation using this equation. So it will be v square by 2g plus h plus z naught. Okay, so this is equation number three. Okay, so we're just rewriting this equation by considering this as h. Okay, so the total head related to the channel bottom, this is called specific energy. Total head relative to the channel bottom, this is called specific energy, and this is represented by E. Okay, so this basically expresses energy per unit weight. Specific energy is nothing but weight per energy per unit weight. So let's say uh, if A is the cross-sectional area and Q is the discharge, so then energy can be related as E is equal to H plus Q square by 2G into A square. Okay. So derivation is not important, and that will be out of the scope of this course. So we'll not be going to derivation part. So this is how you'll be able to relate energy, flow rate, and area of cross section. And this is very important for analyzing a flow in open channel. Okay. And we also have a relation between energy and H as well. Constant discharge. So let's say if the discharge is constant, okay. Let's say Q is the constant discharge or flow rate. So then we have relation between specific energy and water depth. So let me just draw it. So the x-axis is specific energy E, and y-axis is depth of the water. The x-axis is h. So this is the center line. It is y is equal to mx, or y is equal to x, and this is the h varies with specific energy. So this will be tranquil flow, and this is going to be rapid flow. By h critical, and this is E critical. So this is our v square by 2g, that is energy because of velocity, and this is given by q square by 2g into a square. Okay, so this is a velocity will vary, sorry, specific energy will vary with respect to, or height will be varying with respect to specific energy. Okay, the critical point of minimum energy occurs in this entire diagram. It will be occurring. So if there is a critical point, it will be in that point. dE should be dE by dH should be zero, right? The critical point of minimum energy. So this will be occurring at dE by dH is zero. At this location, we'll be having a critical point, right? Critical point of minimum energy. So we just have to differentiate this equation, equation number 4, with respect to H. So it will become dE by dH. Or let me write down the equation first. E is equal to H plus Q square by 2G A square. Okay. So if we differentiate this with respect to H, we'll be getting 1 minus Q square by this is a constant discharge, right? So Q is constant. So this will become G into A cube into dA by dH. This will be 0, which is equation number 5. So if we just solve this, we'll be getting dA by dH as G into Q, sorry, A cube by Q square. This is equation number 6. So from here, you'll be able to calculate constant discharge critical velocity. So when the channel depth at the free surface, let's say it is B, sorry, channel width, not breadth. Let's say if B is the channel width at the free surface. Okay. So in that case, dA will be equal to B into dH, right? Okay. So the critical area is AC, and critical velocity VC becomes AC is equal to BQ square by G power 1 by 3. This is equation number 7. And VC will be Q by AC, right? That will become G into AC by B power 1 by 2. This will be equation number 8. And if you consider a rectangular channel, okay, uh, and consider discharge per unit breadth, that is Q. So let's say Q is discharge per unit width. So then Q will be Q by capital B, right? And we also know that A is equal to H into B, right? Height into breadth. So the critical depth HC makes the specific energy minimum, and that location can be identified as HC is equal to Q square by G, or 1 by 3. Okay, this is equation number 10. So where HC is the critical depth, which makes specific energy minimum. Okay. So the specific energy, let's calculate specific energy in a critical situation, that is when all the quantities are minimum or total head. So at critical depth, that is HC, EC is going to be Q square by 2G HC square plus HC, right? This was obtained from the previous equation. From equation number, from this equation, I'm just changing the variables. Okay, instead of normal Q and H, I'm writing critical values. Okay, so this will become equation number 11. And from previous equation, we also have Q square is equal to G into HC cube. That is equation number 12. Okay, from this equation, I'm just changing the variables. So G square will be equal to Q square is equal to G into HC. Okay, so if you substitute, we'll be getting EC is equal to HC by 2 plus HC, which will be equal to 1.5 HC. Okay, the specific energy in critical situation will be 1.5 times of the critical water depth. Okay, yeah. So let's try to solve a problem. What will be the maximum discharge? What is the maximum discharge for 2 meter? specific energy in an open channel with rectangular section of 5 meters wide. Okay. So we already know that maximum discharge will occur at critical points. So EC, which is equal to 1.5 times HC. This also we just derived. EC will be 1.5 times HC. Okay. So HC will be EC by 1.5. So that will be 2 by 1.5. Okay. Because 2 is already given, right? 2 is the specific energy when discharge is maximum. So it will become EC. Okay. So if you simplify this, it will be 1.33 meters. And also we know that Q square is equal to G into HC cube, right? This is from equation number 12. So just substitute it. Q will be equal to G into HC cube power 1 by 2. So if you substitute all the variables, you will be getting. So G is 9.8, HC we just solved for it. So if you substitute, we will be getting 4.82 meter square per second. So if you want maximum discharge, that is Q, we just have to multiply small q into the breadth of the channel. Sorry, width of the channel. So it will be 4.82 into what is the breadth of the channel? It will be 5. So this gives us 24.11 meter cube per second. Okay, this will be the maximum discharge. Okay, let's also try to solve one more problem. So find the critical water depth at the critical velocity when 12 meter cube per second of water is flowing in an open channel with rectangular cross section of 4 meters wide. So let me write down the question first. Find the critical water depth and the critical velocity when 12 meter cube per second of water is flowing in an open channel with a rectangular section 4 meters wide. So that means this is the width of the channel. So we're asked to calculate critical water depth and critical velocity. So we're asked to calculate these parameters at 12 meter per second, 12 meter cube per second water flow rate. So this is going to be the maximum flow rate. So what is the relation? What are the relation that we have? Hc is equal to g q square by g whole power 1 by 3. This is one relation which relates critical depth to flow rate, and we also have q is equal to q into b. Okay, and for velocity vc will be equal to q by hc. That is nothing but g into hc. Okay, so we have all the values. So q is given as 12 meter cube per second. B is given, that is 4 meters. Okay, so if you substitute these values in this equation, we'll be getting value of Q, right? So if you substitute value of Q in this equation, we'll be getting value of HC. So that should be around zero point 0.305 meters. And from HC, if you substitute this here, from QC and HC, if you substitute here, you should be getting value of VC, that is 1.73 meter per second. Okay. So this is how you'll be able to calculate critical velocities and critical depth. Okay. So do you have any doubts in this? If you have any doubts, you can post them in the chat box, or you can unmute yourself and ask me as well. Any doubts? Any doubts in this section? Either in the problems part or in the concepts that we discussed. Any doubts? Okay, so if you don't have any doubts, then we'll move on to the next topic, that is subcritical and supercritical flow. Okay. So let's say we have obstruction in the field, in the flow of water. So if the flow depth is deeper or shallower than HC, where HC is the critical depth, if the actual depth is deeper or shallower than HC, then flow behavior will be different. So we have two cases. One is subcritical flow. Okay. So when the velocity, or sorry, when the water is deeper than HC, okay, or that means if value of actual depth is higher than the critical value, the velocity will be smaller than the traveling velocity of the long wave, and this is called a tranquil flow or subcritical flow. And then we have supercritical flow. Okay. So when the water depth is shallower than HC, okay, that means H will be smaller than HC. So in this case, H is greater than HC. So in that case, velocity will be larger than the traveling velocity of the longer wave. And this type of flow is called rapid flow or supercritical flow. We just saw this in the EC and HC diagram as well, like during a constant flow rate. We also, wait, let me go back. Yeah, in this equation, we also saw tranquil flow and rapid flow, right? Same thing. So they're also called as supercritical flow and subcritical flows. Okay. So when HC is greater than when H is greater than HC, it will be a supercritical flow or tranquil flow. When H is less than HC, it is called as supercritical flow or rapid flow. Okay. So I guess you must have already seen this animation as well during the lecture. So Professor Shubhata Kumar Majumdar has already showed this. Majumdar sir has already showed this video as well. Okay. So if not, please watch the video, then you'll be able to have a clear understanding about it. constant water bath. Okay. So for case of rectangular water channel, so we derived many equations, right? So for that, let me write down this equation again. E is equal to 1 plus q square by 2g h cube. Okay. The specific energy will be increasing parabolically from 1 all the way to, this is E by h, this is E by h, and this is q by g h cube. Okay, under root. So if you plot a graph between E by h and q by square root of gh cube, the value will vary from 1 and it will parabolically increase from 1 to q. Okay, when the water depth is critical, that is when h is hc. So at that point, q square will be again gh cube and E by h will also be 1.5 because EC is equal to 1.5 times hc, right? So this relation holds. Okay. So must have already, sir, Professor must have already discussed about hydraulic jump as well. So I don't have this animation, so I'm not able to cover that particular topic because if you're supposed to have a better understanding, I think animation would be help, but I don't have animation right now, so I think I have to skip this topic. But I'll just write down the topic name so that if you want to refer, you can refer Professor's lecture, hydraulic jump. Okay, so this is mostly seen in dams. Okay, so whenever it is a phenomena, I'll just explain roughly. So it is a phenomena of flow when fluid or a liquid at high velocities, when it is discharged and it flows into a zone of low velocity, then there will be a rather abrupt rise in the liquid surface. Okay, so this is mostly seen in dams. Okay, whenever there is a discharge, okay, when water is discharged with a high flow rate and it is flowing into the low velocity zone, okay, what happens? There will be an abrupt jump in the or abrupt rise in the liquid surface, right? So this is called hydraulic jump, and in this case, flow will be rapid and it will be unstable. Okay, so if you suddenly reduce the flow or if you decelerate the flow, it will be shifting to a subcritical flow. Okay, or tranquil flow. Okay. So you can, yeah, you can also refer to professor's class once on this particular topic. And if you have any doubts in that, I'll be trying to help you, or I'll try to solve your doubts. So yeah, if you have any doubts, you can ask me. If not, we'll be moving to the problem session. We'll try to solve a couple of questions and then the session. If you have any doubts in this lecture or maybe in the class taught by professor, you can ask me. You can type them in the chat box or you can unmute yourself and ask me. Any doubts? Okay. So if you don't have any doubts, we'll move on to this problem session. Okay, so coming to the first question, in the water channel, the flow behavior is turbulent. Option A, turbulent. B, laminar. Transition. D, ideal. Okay, so in the water channel, we already discussed, it is having a higher hydraulic depth, right? So because of that, Reynolds number will be very high. So if Reynolds number is very high, that means it is a turbulent flow rate. Certainly option one. So in the water channel, the mean velocity u is at dash depth. So 60 to 90%, 50 to 70%, 10 to 40%, less than 15%. So this is it will be at a depth of 50 to 70%. Okay. So coming to the third question, in order to maximize the flow rate Q, the depth of the water channel should be dash of the width. So option A one third, option B one third, sorry, option A half, option B one third, option C one fourth, option D none of these above. So we also solve this, right? What should be the depth? It should be one half of the width. Okay, H should be B by 2. So this we have already solved, right? So coming to the fourth question, water channels have the following characteristics. The channel where a stream of water flows with a free surface exposed to open air. Option B, water channels have large hydraulic mean diameter, mean depth. Option C, in water channels, the Reynolds number is high or large and the flow is turbulent. Option D, all the above. So we know that like this is a definition for a water channel, right? So it is a stream, it is a channel where stream of water flows having a free surface and the free surface will be exposed to air. Okay. And they have obviously because of the larger diameter, sorry, larger hydraulic mean depth, they also have larger Reynolds number. Okay, so that correct answer will be option D, that is all the above. Sorry, we also have couple of questions. Let's solve them. I didn't mention them here, but I'll write them down now. We'll try to answer those questions as well. Okay. Okay. We have a question on Manning. We have fifth question. We have a rectangular channel having a depth of 2 meters and width 3 meters. Okay. So bed slope is 1 in 500. The value of Manning roughness coefficient n is 0.05. N is equal to 0.05 in Manning's equation. I'll just simply write this down. Okay. So the actual sentence is that the value of Manning's roughness coefficient is 0.05. So I'm just putting it in this way. So we have to calculate discharge through the channel. So what will be the discharge? Okay. So what is Manning equation? What is Manning's equation? So it's nothing but V is equal to 1 by n into m power 2 by 3 into I power half, right? And what is m? M is nothing but area by wet surface area, and I is tan theta or sin theta. Okay. And we were given value of n is equal to 0.05. Depth is given, that is h is given 2 meters, and the width is 3 meters. Okay. So we have to calculate flow rate. So how do you calculate this? First, we are supposed to calculate velocity. So how do you calculate velocity from this given data? Any idea? Okay, so we were given that bed slope is 1 in 500. That means for every 1 meter, for every 500 meters that you are going in this channel along the length, you are going 1 meter in the depth. Okay, so that means this is what it was supposed to be. Okay, so we are basically given value of theta. So tan theta will be 1 by 500. So you can directly take this as value of I. Okay, so we have value of I. M is also given basically. So M will be cross section area, that is B into H, that is 2 into 3 by weighted perimeter. What will be the weighted perimeter for rectangular channel? B plus H into H, right? So that will be B plus 2H. That will be equal to what is breadth? Breadth is or width is 3 plus 2 into 2. So this will be 7. So 7. So value of M is 6 by 7. So we have value of M as well, and N is also given. So just substitute them here and you'll be getting value of V. Okay. So once you have value of V, you just need to multiply that with area, that is 2 into 3, and you'll be getting the final flow rate. So if you solve this correctly, value of Q will be 4.85 meter cube per second. Okay. So it's just substituting all the values. Okay. So coming to sixth question, the relation between hydraulic mean depth and hydraulic radius of a rectangular water channel. The relation between hydraulic mean depth and hydraulic radius of a rectangular channel. So is it equal or larger than mean depth is larger than hydraulic radius, or is it smaller than hydraulic radius, or none of the above? So in a rectangular channel, hydraulic mean depth will always be greater than the hydraulic radius. Okay. radius. This is for a rectangular sun. And coming to the seventh question, consider a fully charged flow. Which of the following shape will have a shortest length of the weighted perimeter for a given area? So for a given area, which shapes will be giving shortest weighted perimeter length? Weighted perimeter length. Is it rhombus? So this we have already discussed, right? Is it rectangle? Is it triangle or circle? So this we have already discussed, and the correct answer will be option D, that is circle, right? And coming to eighth question, consider a section. Shape is selected in such a way that the weighted perimeter is minimized. For such a case, the discharge and mean velocity or mean flow velocity, what would be the values? Will it be maximum, minimum, zero, or unity? What will be the values? So this also we discussed for a given shape. If it is having a minimum weighted perimeter, then discharge and mean flow velocity should be always maximum, right? Option A. And coming to ninth question, at large Reynolds number, the friction coefficient becomes. So what will be the value of friction coefficient at higher RE values? Sorry. What would be the value of friction coefficient at higher values of RE? At higher values of RE, friction coefficient becomes constant, right? Okay. So that is it. If you have any doubts, you can ask me. You can post them in the chat box or unmute yourself and ask me. If not, we'll end this session. If you have any doubts, you can post them in the chat box or unmute yourself and ask me. If not, we can end this session. Any doubts? Be it in the theory part or in the questions part or from the previous topics as well. So if you have any doubts, you can post them in the chat box or unmute yourself and ask me. If not, I will end this session. Okay, so if you don't have any doubts, we'll end this now. Okay. Thank you, everyone. Thank you for attending the session. Let's meet on next Tuesday. Thank you.